Hello everyone. After the introduction to the oxygen binding proteins, we'll start the introduction towards hemoglobin, which is the most commonly found oxygen binding protein. Before getting into the hemoglobin, the macrocycle that makes up the hemoglobin is porphyrin, which is derived from porphin. So in the last video we have seen 4 different macrocycles where the porphin has been shown. Now we'll also discuss some more details about this porphin ring. Along with the substitutions we call it as porphyrin. So within this porphin we can see the labeling has been shown right from 1 till 24. So this macrocycle positions are labeled from 1 to 20, and then the positions 21, 22, 23 and 24 are being taken up by nitrogens. There are 11 double bonds that are in conjugation, and the 2 resonance structures have also been shown. What exactly is porphyrin? In Greek, porphyrin is related to color purple. Purple is a combination of blue and red. Well, all the 11 double bonds are in conjugation, and this porphin or its derivative porphyrin is considered to be aromatic with 22 pi electrons. Also, 2 lone pairs of 2 nitrogen atoms of this macrocycle also involve in conjugation. Completely it makes 26 electrons. Even with 26 electrons that are in conjugation, it is still an aromatic system. So Vogel has proposed that the aromaticity of porphyrin is related to an 18 aniline. Now, if there is any evidence whether it is aromatic or not, we get it from NMR spectroscopy. In NMR, whatever protons that are present in the periphery, these protons resonate downfield, whereas the inner protons which are present over the nitrogens, these protons they resonate strongly upfield. So it is a very clear indication that the given macrocycle is aromatic. When it comes to these porphyrins are considered to be weak bases, or they could also be considered as the weak acids. When it acts as weak bases, these 2 nitrogens can also get protonated, where it acts as a dication. As weak acid, this porphyrin can lose these 2 hydrogens or these 2 protons, thereby acting as a dianion. But in most of the biomolecules, we see porphyrin as a dianionic species. For example, if iron enters or the magnesium enters into the chlorophyll, iron or magnesium is present in +2 oxidation states. Also, we see that in this porphyrin, the 2 hydrogens are situated at 21 and the 23rd position, but not at 21 and 22 position. The hydrogen could also be present at 21 and 22. These 2 hydrogens are not static, instead they are dynamic. These 2 hydrogens jump over the 4 nitrogens. But the most stable tautomer being the trans tautomer, which is 21 and 23H tautomer. This is energetically preferred to the cis tautomer, which is considered as the 21 and 22H. So these hydrogens are not static, they are dynamic and they jump. This porphyrin, it is a square planar core. As I said, it is aromatic with 26 electrons. So these porphyrins are generally substituted on the periphery. These are the periphery, these are the internal positions, these are the peripheral positions. At the internal positions, no substitution is possible, but at periphery, substitutions are possible. So these internal positions are called as alpha positions. Altogether there are 8 alpha positions. In the periphery there are 12 positions. Out of these 12 positions, 8 positions which are part of pyrrole rings are called as beta positions, whereas the 4 methane bridges that are connecting the porphyrins connecting the pyrroles, these are called as mesopositions. So altogether there are 4 mesopositions, 8 beta positions that could be substituted, and 8 alpha positions which cannot be substituted. The most frequently encountered substitution pattern is, now these are beta positions, altogether 8 substitutions can be done at beta position, so we can call it as a beta octa alkyl porphyrins. Whereas when it comes to the meso, mostly aryl substitutions can be done at meso positions. We call it as a meso tetra aryl porphyrins. But whatever porphyrins that occur naturally, all are beta substituted. They are not meso substituted. Naturally occurring porphyrins are only beta substituted in an unsymmetrical fashion. One of the best examples for the unsymmetrical fashion is the porphyrin. Now in this case we can see that all the beta positions have been substituted, but not in a symmetrical manner. It is completely in an unsymmetrical manner. These porphyrins are strongly colored compounds. The color is mainly due to some charge transfer transitions. Now this is the macrocycle which is present in the hemoglobin. Well, suppose if I choose a living organism, a human being, the amount of iron present in hemoglobin on an average is about 2.6 grams within the hemoglobin. What is hemoglobin? Hem is considered as blood in Greek, whereas globin is considered as protein, but no more. Now hem is considered to be as blood. It is that portion where the porphyrin is surrounding the metal, but in older years it was called as blood. Hemoglobin, it can be seen almost in all vertebrates and some of the invertebrates. In hemoglobin, porphyrin will behave as a dianion. Now we can see that at second and third positions we have some substitutions. At second position we have a methyl substitution, whereas at the third position we have a vinyl group. With these substitutions we are calling it as a porphyrin. Suppose if one of the substitutions, if one of the vinyl groups at third position, if it is replaced by a CHO group, we are just making only one substitution in the whole of the porphyrin, and once such a substitution is done, the color of the pigment is found to be a pale green one. No more it is a red color one when iron is present along with a vinyl substitution. But if at all that vinyl substitution, if the vinyl is substituted by a CHO, then the pigment is called as a chlorocruorin. This chlorocruorin is present in the blood plasma of many annelids, and the affinity for this chlorocruorin towards oxygen is very much weaker when compared with the most of the hemoglobins. So just one substitution can change the whole chemistry of a oxygen carrying protein. Also chlorocruorin, this is called as a dichromatic compound. Chroma was related to color in the older years, so dichroma meaning it can show up two different colors. It appears in green color in very dilute solutions, whereas it appears as a light red color in concentrated solutions. So appearing as green in dilute solution, appearing as light red in concentrated solution, therefore this chlorocruorin is called as a dichromatic compound. Hemoglobin, it is a tetramer. Altogether there are 4 subunits. This hemoglobin contains macrocycle porphyrin along with the iron. When it comes to the iron, there is approximately octahedral environment around the iron. So the iron that is present at the active site, it could be present in +2 oxidation state, or it could be present in a +3 oxidation state. When it is present in +2 oxidation state, it could be a high spin or it could be existing in a low spin state. For a D6 high spin state, the configuration in octahedral environment is T2G4 and Eg2, whereas in a low spin state it is T2G6 and Eg0. Since there is unsymmetric electronic arrangement, distortions are expected, whereas in this case the T2G shell is completely filled. There is no unsymmetry in the electronic configuration, and hence no distortions are expected for this configuration. When iron is present in +3 oxidation state, again it could be existing in a high spin or a low spin state. In a high spin iron 3+, T2G as well as Eg are half filled, therefore symmetric electronic configuration is present and no distortions are expected for iron 3+ high spin state, whereas iron 3+ low spin state has some unsymmetry associated with the T2G. This is about the iron. When it comes to the oxygen could exist in a dioxin form, O2, where it could be a triplet state or it could be a singlet state. It could also exist as a superoxo form, or it may also exist as a dioxo form. So such an oxygen could associate with the iron to give different oxygen binding proteins. This is some introduction about the hemoglobin microcycle that is present, and also the metal atom that is present at the active site of the biomolecule. In our next video we will be discussing about hemoglobin.